Let's talk about duality in linear programming. Duality is the most fun topic, in my opinion, that you'll see in this class. It's the closest thing, in my experience, to magic in the field of optimization that I have ever seen. It's an extremely important, interesting concept. It lets you do more with a linear program than just solve it. Right? That's an important step. It's probably the most important step. But once you solve a linear program, there are other questions that start to emerge from that. You could say, for example, what constraint is hurting me the most at the optimal solution, right? If you work for a company and you want to look at what you're doing, you can say, once you've solved your allocation problem, once you've solved the optimization decision you're trying to make, you might say, all right, of all these limits that are hurting me, what is the limit that is hurting me the most? What would I like to change, right? What resources would I like to have in addition to what I already have that could make me even more efficient? You could say, which objective coefficient affects the outcome of my linear program the most, right? I might be able to say, if I were to charge more for one of these products, would it affect my bottom line more? And so on and so forth. So it's like a post-mortem analysis or a meta-analysis where you look at the solution and you make insights about the solution itself. And the whole solution here, the whole analysis of this, centers on this mathematical principle that says that if you give me any linear program, there is a dual linear program. There's a new linear program I can invent that is related to the original linear program in the following ways, which all sound really strange at first. Number one, every variable in the original linear program now becomes a constraint in this new linear program, which we call the dual. The original linear program, the one you start with, you call that the primal. Okay, the primal linear program is just the original problem that you begin with. So every variable in your original problem now becomes a constraint. And equivalently, every constraint in your original linear program now becomes a variable. So we flip these things, and it doesn't make any sense yet, right? I haven't explained how this transformation actually works. The objective function coefficients, the vector of objective function coefficients in your primal, become the constraint coefficients, or the right-hand side in your dual linear program, and the constraint coefficients, or the right-hand side of your original linear program, now becomes an objective function. Okay, none of this is going to make any sense right now. Okay, but I'll give you some examples and you'll see. And we're also going to unpack the relationship between this primal and the dual the primal and the dual linear program. And it looks like this. So if you give me a standard form, for example, linear program like this one over here, minimize C transpose X, AX is equal to B, and X is non-negative, the dual linear program looks like this thing over here. So what have I done? I've taken that B, that vector B, which was my right-hand side, I've taken that vector B and I've moved it over here. Now that's my objective function vector. I've also made a maximization objective instead of a minimize, and I called my variable here y instead of x. And then what else is true? Before I used to have ax is equal to b, and now I have a transpose y is less than or equal to c. But actually all of my variables no longer have non-negativity. So you can see both of these linear programs are completely determined by A, B, and C, but they're like transposes of one another, right? Like mirror images. Let's do this with some numbers so you can see what's going on. So here I've got a linear program that looks like, in fact, I'll do this one by hand so you can see it. I'll copy it down really quick. We've got minimize 2, minus 3 and 6, 2, minus 3 and 6, and I'll do 2x1 minus 3x2 plus 6x3, subject to, and then 4 4, 5, 7 is equal to 9. 4x1 plus 5x2 plus 7x3 is equal to 9. And then a 1 and a 2 and a 0. 1x1 plus 2x2 plus, and I'll do plus 0x3 just so you can see it. 0x3 is equal to 1, and all non-negativity. x1, x2, x3 are non-negative. Okay, I'll construct this dual by hand. The first thing I'll do is I'll take this matrix here, the constraint matrix, and I'll transpose it. So all of the rows become columns, and I'll do that now. I'll do 4 and 1, and 5 and 2, and 7 and 0. And now I'll take the constraint coefficients, or the constraint terms, and I'll bring them over here into the objective function. So that's a 9 and a 1. And then I'll take my original objective function, 2, minus 3, and 6, and I'll bring that over here, 2, minus 3, and 6. And now I'll put in my inequalities as they were prescribed, and now I'll just put in my y's. 9y1 plus 1y2 subject to 4y1 plus 1y2 less than or equal to 2, 5y1 plus 2y2 less than or equal to negative 3, 7y1 plus 0y2 less than or equal to 6, and this is a maximization problem. So maximize this over y1 and y2. Okay, this is the primal, the letter P, and this is the dual with the letter D. Okay, now I've constructed these two linear programs. I haven't established any kind of functional relationship between them, right? And we wouldn't expect there to be one, but there actually is, and it's pretty incredible. We'll begin with something that's not so remarkable. It's called the weak duality theorem. Okay, and the weak duality theorem says that if x is feasible for your primal problem, which we started with being in standard form, the primal problem, which was minimize a standard form problem, and y is going to be feasible for the dual problem, the maximization problem, then C transpose x is always greater than or equal to B transpose y. Okay. So in particular, the minimization problem, which was C transpose x, is always at least as big as the maximization problem. So this is always true for any feasible points in the primal and dual respectively. How does that proof work? Not so difficult. It goes like, I'll begin by writing out that standard form linear program once again. In both of those, so with the primal was minimize C transpose x subject to A, x is equal to B, and x is greater than or equal to 0. And then the dual problem was maximize B transpose y subject to A transpose y is less than or equal to C. Okay, that was my, I'll do a little primal, a P, and then a D over here for dual. Okay, so what is true about this? So we've got C transpose x. So we want to show that C transpose x is greater than or equal to B transpose y, right? This is our goal here. So how does this work? Well, C transpose x, what is true about this? We have A transpose y is less than or equal to C from this constraint here. And since x is all non-negative, we therefore know that C transpose x has to be greater than or equal to, substitute an A transpose y for that C there. So that's A transpose y transpose x. And that, of course, is just equal to, following the laws for transposition, that's y transpose ax. And then ax, of course, is equal to b because of our standard form linear program. So that's equal to y transpose b, which is b transpose y. So therefore, C transpose x is greater than or equal to B transpose y. All right, the minimization problem is always at least as big as the maximization problem. So that's weak duality, okay? Tells you that there's some relationship here, and kind of a direct one that we were able to extract. In fact, there's a stronger statement as well, the strong duality theorem, that says if you have an optimal solution x star for the primal problem and an optimal solution y star for the dual problem, then in fact those objective values are equal at optimality. Then C transpose x star is equal to B transpose y star. We might visit the proof of this later and work through that. You can do it either using simplex tableaus or what's called Fourier-Motzkin elimination. We might touch on that, but we won't do that right this second. So that's kind of interesting, right? It tells me that if I were to take that problem, if I were to take this problem here, in fact, why don't I show it to you right now? If I were to show you this problem here, this is that primal and this is the dual that we computed before. Turns out the optimal objective value for either one of these happens to be 57 on 14, and here are the optimal solutions, x star and y star. So that's kind of a big deal, right? It tells me if I solve the one problem, I already know what the objective value is going to be for the other. In fact, you can even use what's called complementary slackness to figure out what the actual optimal solutions are, and we will learn how to do that. But for now, you can just trust me. What this accomplishes, it turns out, is that you can derive all kinds of cool insights about various problems, and we'll look at some examples of that. Before I do that, though, I want to say that this is not at all confined to the domain of standard form problems. In fact, we can take the dual of any kind of linear program. Minimization, maximization, constraints could be inequalities, or variables could be negative or positive or whatever we like, and we'll look through an example of how this works. I want to point out that duality is a reflexive property, which is to say that the dual of the dual is the primal. So if I take a linear program and I take its dual, and then I take the dual of that again, I get the primal. I recover the original problem. So it's not like you can keep taking duals of things. A lot of people get confused by this table when they first see it. So I'm going to work through an example now where you can see how we would apply this table and how this works. So we've got here a primal problem that looks like the one you see here. So let's copy this down. So notice that it has 4 linear constraints and 3 variables. So 4 constraints, 3 variables. So the dual problem is going to have 3 variables, or 3 constraints and 4 variables. So first let me copy this problem down, and we'll see where all these various terms come in, and so on and so forth. So this is a minimization problem. It says minimize 2, minus 3, and 6. So 2, minus 3, 6. And then I'll run down these columns. 4, 5, 1, 1. So 4, 5, 1, 1, like that. 4, 5, 1, 1. The next one is 5, minus 8, and 2. 5, minus 8, and 2. And then a 0 below that. And then a 7, and then 2 zeros. And a 7, like that. And then the right-hand side is 9, 3, 1, 4. 9, 3, 1, 4. And then our sign constraints say that x1 is non-negative and x2 is negative. X1 is greater than or equal to 0. X2 is less than or equal to 0. And then x3 is going to be free. Whenever you don't see a sign constraint mentioned attached to a variable, it means. And what I'll do next is I'll fill in with I'll write in the variables. So x1, 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 x1. You don't actually need to write these variables in because it's kind of, evident from writing them, but I'll do that now just to make sure we're completely clear on everything. x2, 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 x2. I really don't need to write out the variables that have a 0 coefficient. So that's really useless. It's almost It's almost bad teaching practice to do that because you can mislead people, but I'm going to do that now anyway, just so we've got everything written out. And what else do I need? The directions of the constraint inequality. So I've got an equal sign for the first one, greater than or equals, less than or equals, and an equal sign. So, okay, you just watched me copy down the exact contents of the slide. So what's the point of all this? Now we're going to refer back to this table, and I'll show you how this works. So this table here is something you're going to use a lot. And the way this works is, in this case, we started with a minimization problem. I'm going to take the dual of this. And so if you start with a minimization problem, you would look at the things that happen in this left column and then look at what they correspond to in the right column. Okay, so what are some things that we know first? First of all, we know that the original matrix A now becomes A transpose, as we saw in an earlier example. So I'll do that now. I'm going to write out that, that constraint matrix here, this thing. I'm going to transpose that, and I'll write those terms in. So the first column is a 4, 5, 1, 1. And so I'll do that. 4, that becomes a row. 4, 5, 1, 1. Second column is a 5, minus 8, 2, and a 0. And third is a 7, 0, 0, 7. Good. And then I have the C in my original problem. If you look here, you can see that C, the objective function, now becomes the right-hand side of the constraints. And so that means my objective function vector here, 2, minus 3, and 6, goes over there, 2, minus 3, and 6. And next, what is also true? What is also true is that the objective function of my new dual problem is B, which is the constraints, or the right-hand side from my constraint vector. And so this is now going to look like 9, 3, 1, 4. And also the primal problem was minimized, so the new one is maximized. And so we'll write a little maximize there, like that. And in my primal problem, I had, remember, 4 constraints and 3 variables. So I had constraint, 1, 2, 3, and 4. And I had 3 variables, x1, x2, x3. And as you can see here in my new problem, there are clearly going to have to be 3 constraints, 1, 2, and 3, corresponding to x1, x2, and x3. And 4 variables, which I will call y1, y2, y3, y4. Let's write in all those y's there again. y1, 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 y2, 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 y3, 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 y4, 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 and I'll add in my little plus signs here, like that. All right, what else needs to happen? So I've established a maximization objective. I've got my right-hand side here. What else needs to happen? I need to fill in the direction of the constraints, whether they're equals, less than, or greater than for these constraints. And I also need to figure out the signs of my variables. Are they positive, negative? What are the constraints on those? And you recover those from this table as well, and they look like this. So here's what you would do. You would look at this table and you would say, for my constraint, I see that anytime a constraint in my primal problem has a greater than sign, it means the corresponding variable also has a greater than sign in the maximization problem. Okay, and so what that says, for example, is my second constraint has a greater than sign in it. So if my second constraint in my primal has a greater than sign, it means my second variable in the primal has to have a greater than sign. Therefore, y2 is greater than or equal to 0. Okay. Equivalently, if you have a less than sign in a constraint in the primal, that gives you a less than sign for the corresponding variable in the dual. So in that case, I have a left-hand side in my third constraint, which therefore means that my third dual variable has got to be less than or equal to 0. Okay, and what is last? The last one is that if I have an equal sign in a constraint in my primal, that means the corresponding variable is free. And which one is that? That's going to be y1 and y4. So y1 is free and y4 is free. Okay, good. Now the last thing I need to do is figure out the direction of these inequalities here. And we'll do that here by this last little block of this chart here, which says that for a variable in my primal, if I have a non-negative variable in my primal, it means I have a less than or equal to sign in my constraint. So I have x1 has to be greater than or equal to 0. And therefore, so my first variable out of the 3 in my primal, x1, x2, x3, the first one of those has a greater than or equal sign, greater than or equal to 0, which means the constraint has a less than or equal sign in it. My second variable in the primal, x2 less than or equal to 0, has a less than or equal to 0 sign like that, and therefore the corresponding constraint has a greater than sign, so I'd put a greater than or equal to sign like that. Finally, x3, my third variable, x3 was free, which means that my third constraint has an equal sign. So that's the dual. That is the primal, that is the dual. I've just worked out the dual of a linear programming problem by hand. I want to emphasize there's nothing clever I did here. It was simply following the rules. So there's nothing creative about taking the dual of a problem. It's not like there's different ways of doing that. So here's the solution that's written up there. 4 variables, 3 linear constraints, just as we expected us to have. I've also got some MATLAB code if you'd like to play with that, but we don't think we need to talk about that right now. We can do that in lecture. Now what we're going to do next is a lot of fun. What becomes really interesting is when you take a linear program that comes from a problem that you understand, where you understand what the variables correspond to, and you know the interpretation, and you take the dual, and then you try and construct a story around that, right? Why is this a natural thing to do? Well, we can prove mathematically that the objective values are the same, right? That tells you that there is some kind of connection between these two problems, and we're going to look very carefully at and define precisely, or we won't define it, we'll discover what exactly that relationship is. But you can say that because mathematically we know that there's a connection between them, it makes sense that whatever that dual problem is, it's probably something that is useful to us in terms of that original problem. So let's try an example of this. The first one will be the production planning problem. Remember this one? This is where you had the baker who was making different kinds of cake. And so we have the ingredient list here. Remember, you have $3 for every vanilla cake, $5 per chocolate cake you can sell. The baker has these many amounts of these ingredients at their disposal, and then this is how much of each ingredient the cakes require. Okay, and the linear program for this is, as I'm sure you remember, looks like this. You're trying to maximize, you have a variable for each cake, right, vanilla and chocolate, so 2 variables. Maximize the amount of money that you make with these constraints that say that the amount of that each resource that you use can't exceed the amount of the resource that you have. Okay, so we did that, and then we solved the problem, and we got whatever the solution happened to be, saying make this many vanilla cakes, this many chocolate cakes. Let's make things a little simple. We have an awful lot of constraints up here, and I don't want to get writer's cramp, so we'll take a smaller linear program that still has the same structure. This would be some crummy bakery that doesn't use eggs in their or doesn't use flour or something like that in their in their cakes. So it would look like this, and let's take the dual of this problem. I won't bother to do it by hand. I think you can probably trust me, although I think I will refer to that table. So here's our baker's problem, and what do I want to point out here? There's a few notes that I'll make. Number one, we start with the maximize here. And so if your primal has a maximization in it, then your dual problem is going to have a minimize in it. Okay, what else do I want to say? We have 2 variables here, x1, x2, which means that the dual is going to have 2 constraints, as it does here. looks like we have five, 5 constraints, which means that the dual problem now has 5 variables, y1 through y5. What else do we want to say about this? We have non-negativity for our variables. And if we go back to that table there, I can show you that if you have non-negativity constraints in a maximization problem, let's erase all this here. If I have a maximized problem that has a greater than or equal, a non-negativity for the variables, it means that the corresponding constraint also has a greater than or equal sign in it. And so what does that mean? It means when we take the dual of this Baker's problem, it means you're going to have inequalities going in this direction. And then similarly, I won't bother to flip back through that table again, but in your maximization problem, if you have inequalities like this, if you have less than signs, it means that the variables have non-negativity on them. Okay, so this is what the dual of this Baker's problem looks like. Okay, you've got a variable, you've got a minimization objective, and you have a variable for every constraint in your original problem. Okay, now what we're going to do is, this is a good time to pause the video and try and unpack what on earth this problem could correspond to. And we know it corresponds to something because we know that the optimal objective value of this problem is equal to whatever the optimal objective value was of the original problem. So it tells you something about it. But we're going to look at this problem and say, what does it mean? Who is trying to solve this problem? Why is it important to them? I'll talk about this a little more and we'll try and work this out. The first thing you'd want to look at here is that your variables here correspond to the different ingredients that the baker has. Why is this? It's because every constraint in the original problem came from an ingredient, right? It's a limit on how much sugar you have, or how much butter, or how much flour, and so on and so forth. It's a limit on that. Okay, so every you had 5 constraints in this original problem, this primal problem. So therefore, there's 5 new dual variables here. So you have a variable for flour, a variable for sugar, a variable for butter, and eggs, and so on and so forth. You've never got a variable for that, which is a little strange. And now also you have a constraint for every original primal variable, right? And in our original problem, we had a variable for vanilla cakes and a variable for chocolate cakes, which means in my dual problem, I have a constraint corresponding to the fact that vanilla cakes exist and a constraint corresponding to the fact that chocolate cakes exist. Okay, what the heck is going on here? The best way in my experience to try to work out what this connection is first to say, well, strong duality it holds here, right? In other words, we know the objective value, the optimal objective value of this problem here will be the same as the optimal objective value for the original problem. Now, given that we know that, in particular, it means that the units have to line up, right? Whatever the units are of my primal problem, they have to be the same as the units of my dual problem. Now, what were the units of my objective function? I was trying to maximize money, right? So the units were just dollars. I was trying to maximize the amount of dollars I take home. Therefore, the objective value of this thing here also has to be in dollars. Okay? So if the overall objective function has to be measuring dollars, we can ask then, what do the variables represent? What do the variables represent? To work that out, we have to work out what these numbers mean. These numbers here represent how much of the ingredients you have. So we've got 41 and 24. I want to see which ingredients those were, 41 and 24. We had 41 cups of sugar and 24 cups of butter. So it's sugar and butter, and I think eggs is probably the next one. So sugar and butter and eggs. And so what does that mean? Let's write out the objective of this dual. You have 41 cups of sugar. I'll just do this. I'll just 41. Yeah, okay, I'll do it that way. I like that. Cups of sugar. times y1 plus, and then the next one was 24, I think it was cups of butter, times y2, and so on and so forth. And this has to all be measured in terms of dollars, right? Because the objective values line up, and therefore so do the... And so therefore what has to be true? So what are the units of y1 then? The overall objective function has to be measured in terms of dollars, and therefore 41 cups of sugar times y1 has to be something measured in dollars. And therefore, what is y1? y1 has to be dollars per cup of sugar. And equivalently, y2 has to be dollars per cup of butter. Y3 is dollars per egg, and then I think y4 is vanilla, and I don't remember what y5 is, dollars per vanilla. Okay, what do you call that? What do you call something that is dollars per amount of something? You could pause the video if you'd like. When you talk about dollars per cup of sugar, we call that a price. We call that a unit price. It's how much you have to pay for a certain amount of something. So therefore, we can say the dual problem is asking you to talk about prices, right? The dual problem is saying your objective is not making cupcakes. It's not buying things. It's setting prices, okay? Like you're making an offer for something. So the objective, the dual problem involves naming a price for something, okay? Why would you be naming a price for something? Let's see what's going on here. Well, what does this mean? You are someone who's showing up and you are inventing prices. Okay, you're inventing prices for each of the ingredients that this baker has. And so what does the objective function now measure? This is 41 times y1. Remember, 41 is how much sugar that baker had to begin with, right? So 41 times y1, that is the value of all the sugar in that bakery under this price that you were inventing. Okay, equivalently 24 is the amount of cups of butter that the baker had, and so 24y2 is the value of the butter in that baker's possession. Okay, so overall the objective value is measuring the total price of the baker's ingredients with respect to these prices, which again you are inventing, right? You are choosing that. So it's the total value, I should say, of the baker's ingredients with respect to these prices that you're inventing. Now, you are minimizing over this. This is like you're saying you want to make the value of the baker's ingredients as small as possible, right? You want to come up with prices that devalue the baker's ingredients as much as you could. Now, why would you want to do this? I don't know, maybe if you're trying to buy the bakery. If you're making an offer to buy the bakery, you'd be trying to lowball the baker by getting everything at the lowest price possible. So you're trying to invent prices that minimize the aggregate value of this bakery or the ingredients therein. Okay, so why can't you just make everything zero and say the bakery is worthless? Well, you've got these constraints that come in. Okay, and what is the significance of these constraints? You've got a constraint for vanilla cake, and you've got a constraint for chocolate cake. Well, let's look at each of these. So what's going on here? What is this? These are the amount of each ingredient that goes into a vanilla cake, right? It's 0.7, it's 3/4 of a cup of sugar, half a cup of butter, and so on and so forth. Okay, so what is this? This is you take the amount of ingredients that comprise a vanilla cake, and now you price them according to these prices that you've made, right? What is this? This is now the value of the ingredients needed to make a vanilla cake. And I've said that value has to be at least 3. Why does it have to be at least 3? Think of it as if you're trying to buy this baker's bakery. Okay, that's the secret about this dual. That's what it corresponds to. It means you're trying to purchase or acquire this bakery. And you're going to look at this and you're going to say, okay, I want to make the cheapest offer I can to this baker to buy it, because why would I want to spend more money than I have to? And you're going to say, well, I have to I want to make the smallest offer that I can. I want to lowball it, but I want the baker to actually accept my offer, right? That's important. I could just offer them nothing, and of course the baker would not take it. So what does this mean? It means I have to be competitive with whatever means of making revenue the baker already has. And so that's what these two constraints represent. Look at these. Look at what this constraint says. This thing here, this is the value of the ingredients for a vanilla cake according to the prices that I am setting forth. Okay, let's suppose that was $2.50. If that was $2.50, then the baker would say, I'm not going to accept your offer. I could make $3 by making these vanilla cakes and selling them. I'm not going to accept the offer that you're making if your offer would lead to the valuation of one of my vanilla cakes as being only $2.50. Okay, and the thing for the second constraint is precisely the same. This is just the same statement, but for chocolate cakes. And that's what the dual problem represents. It's like a mergers or it's an acquisition. This is the interpretation, just to make things totally clear, is the following. Someone shows up and they say, I want to buy this bakery. They say, I want to buy all of the ingredients you have in this bakery. I don't want to buy your cakes. I'm not interested in those. I'm not going to even make cakes anymore. I'm going to use these ingredients to make something entirely different. But I'm going to make the cheapest offer I can to buy all the ingredients in this bakery. And there you're going to say, okay, so then what is, or rather, if you're going to make this offer, you have to come up with prices and say, okay, here's how much I'm willing to buy your various ingredients for. Okay, and so you'd want to make the cheapest offer you could, hence the minimization objective. You want to minimize the total value of all of the ingredients that the baker has with respect to your pricing scheme. But that offer has to be competitive with whatever the value is that the baker could get by making the cakes they already do. And that's what these constraints represent. Each of these constraints says whatever the value is of the ingredients in a vanilla cake, it has to be at least as much as what the baker could get for a vanilla cake. Now, if I was really being more precise about this, I'd have models that factored in, labor costs and, the amount of time you need to spend to run an oven, and there'd be all kinds of other resources that go into that, square footage, real estate, all this sort of thing. And we could put those into this model. There wouldn't be anything hard about that, but for simplicity's sake, we'll avoid that. So that's the dual of the baker's problem, and it corresponds to what you'd call a minimum acquisition price, so coming up with a price that is as cheap as possible, but such that the baker is never disincentivized to take it. And so strong duality here says that whatever that value is, that if I want to buy the baker's bakery, whatever the optimal price is, the optimal total value, it's going to be exactly equal to whatever the baker could get by selling vanilla and chocolate cakes. So there exists a means of coming up with prices such that the baker would be completely indifferent between selling the bakery and selling these vanilla and chocolate cakes. We'll do the same thing here, or what we're going to do now, rather, is not the same thing, but we'll look at this from a slightly different perspective. Now we're going to try inventing a problem where the primal is more like this problem of acquisition that we just talked a moment ago. So we'll begin with the proverbial dude on Craigslist who is selling his home theater system, and he's got a Blu-ray player, a set of speakers, a TV, a PS. That should be a 5, shouldn't it? A PS5 and a lounge chair. Okay, five items. And he doesn't list prices for anything. He says, make me an offer. Okay, there's a big, there's a big, make me an offer sign. And you want everything. You say, okay, I want all that stuff. I want to buy it. And I'm going to make him some kind of offer. I don't know what it'll be. And you email him and say, okay, is your stuff still for sale? Yes, all of it is. You say, okay, well, give me a ballpark. What am I looking at here? And the baker, there's no longer a baker here. It's a dude on Craigslist. he says, okay, here's what I've received, these offers. Someone has offered me $337 for just the Blu-ray and the PS4 slash PS5. $879 for the Blu-ray speakers and TV, $403 for the Blu-ray and speakers, yada, yada, yada. Okay, these are the offers that this Craigslist guy has already received. And your goal is to say, well, okay, I want to make an offer that is, at least as good as any of these for all of his things. So we want to make him an offer he can't refuse, meaning we want to come up with prices for each of these individual items. So we'd like to say, here's how much I'm going to pay for each of the items that you're selling, and therefore the eventual offer is the total of all of that. And I want to make it so good that he can't turn it down, because it has to be at least as good as the offers that he's getting for each of those bundles. Okay, so yi will be the price I set for item I. There were 5 items, so there's 5 variables. And I'd want to minimize y1 summed through y5, so the price for each item. And my constraints look like this, right? y1 plus y4 is greater than or equal to 337. Because the Craigslist guy got 337 offered for the Blu-ray and the PS5, which was items 1 and 4. Okay, equivalently, for each other offer that the Craigslist guy has received, you get these other constraints here that show up like that. Okay, so you can solve this problem. You can plug this into Julia, Python, CDX, MATLAB, whatever you like. You can solve it, and you'd find this solution here. 359 for the first item, 317 for the second, 369 for the third. Oh, and just throw in the last 2 items for free. Okay, sounds counterintuitive, but if you price things in such a way, indeed, you can verify that it actually is totally competitive with all of the offers that this guy is already getting. And so eventually you add all these numbers up, your total offer should be $1,045. You'd say, okay, I'd like to pay you $1,045 for everything you've got. And the Craigslist guy says, well, itemize that stuff. Where are you coming up with that? And you go, okay, $359 for the first item, $317 for the second, and so on and so forth. And sure enough, you can verify this is competitive with all those other offers out there. And I think one thing I want to point out is that this problem here that we formulated is identical in form to that acquisition problem for the baker's problem, right? It was a minimize, and then you had greater than or equal signs for all of these things here. And what you're doing is exactly the same as what was going on in that dual of the production planning problem. And just for fun, we could take the dual of that, and what are we coming up with? A natural way to think about this is that now we have a variable for each of the offers that the Craigslist guy received, right? 6 offers, 6 variables. And what is going to be true about this? Well, think of the variable as being as representing a 0 or 1, let's say, whether you accept the offer or not. Now, to be fair, we haven't talked about variables that are, restricted to be 0 or 1. This is a separate issue, but we'll think of the variables as being of that sort. And so it has to be true. So the value of the offers that you accept is going to be 337 for the first offer, then you accept it or you don't, and 879 for the second offer, which you accept or you don't, and so on and so forth. And then you could say, well, what's true about this? Well, I said x1, x2, x3, x4, x6 is less than or equal to 1. Where does that come from? That is a constraint that arises because the first item that this Craigslist guy is selling is the Blu-ray player. And that Blu-ray player appears in all of the constraints except for the 5th, right? You got 1, 2, 3, 4, and then no 5th, and then the 6th one. Okay, so the first constraint comes from the Blu-ray player here. It says you can't accept more than 1 offer involving a Blu-ray player, right? Because I've only got one. I've only got 1 Blu-ray player, so that goes to someone. I can't accept 2 of the offers that involve the Blu-ray player, or I'd be cheating someone. Okay, equivalently, the second constraint here is associated with the Let's see what that one is. I can't even remember. It's a set of speakers. It's a set of speakers, and the speakers appear in the second, third, fourth, and fifth constraint. And so therefore, we're going to say that the sum of x2, x3, x4, x5 is less than or equal to 1. Okay, and then equivalently for these other three constraints here, they just come from the different items that the Craigslist guy has, because you can't, again, you cannot accept more than one offer that involves the same item, right? Two offers that both request the Blu-ray player, I can only accept one. Now, because we don't know yet, or we haven't yet talked about how do you model a situation where you either accept an offer or you don't, where it's binary 0 or 1 kind of thing. More to the point, rather, these items are useless if they're divided in half. So once I solve this problem, what you actually get is zeros for the first three. So don't touch these first three offers at all. So no x1, no x2, and no x3. We're not going to touch those. And then it says you set 1/2 for x4 and x5 and x6. Now, this isn't practically of any relevance to us. This doesn't mean anything, right? Because it has you accepting half of an offer. So this is not realistic because half a TV is useless. It's a shortcoming of the model because we're using a linear model. Once we talk about integer programming, this will all make sense, and we'll understand how to deal with variables that have to be zeros or ones. But for now, I hope that this is at least enough that it gives you some sense of what's going on. I originally thought about making this Craigslist example involving someone who was selling like bulk items, like a barrel of gummy bears or something, and you could give them half of the barrel of gummy bears or this kind of thing. But it just got really strange, and so I thought this was an appropriate mix of